when I tried from the calendar, it showed Colonel Bhaskar. So I disconnected that, and then I used the other links we sent to for each of us speakers. So
Okay, not a problem.
yeah.
So we are live right now, and the session will start in another 2 minutes.
Okay, great.
Appreciate. Thank you all.
Thank you. Good luck to all.
Yeah.
Thank you.
Colonel, we can get started, sir.
Okay. Good morning, Americas. Good afternoon, Europe. Good evening, India. And my friends down under. This is the first Indo-American webinar in the MasterClass Webinar Series organized on smart water reclamation and reuse experiences from India and the United States by Smart Water and Waste World magazine. I welcome all the presenters, Dr. Berrin Tansel and Dr. Srinivas Rao from the United States, Dr. Pradeep Kalbar from IIT Mumbai, and I am your presenter also and moderator from Mumbai, India. My name is Colonel Bhaskar Tatwawadi, and I call myself a water reclamation enthusiast. This session will be presented by the presenters. At the end of each presentation, there will be a couple of questions to the presenters. Thereafter, after first two presentations, we will have a 15 minutes question answer session in which the audience questions will be taken up. Thereafter, we will have the second part of the presentations by two remaining presenters, again followed by a long question answer session for about 30 minutes. So that is how we intend to conduct this webinar, the Indo-American webinar on smart water reclamation and reuse experiences from India and the USA. And I present to you our first esteemed presenter, Dr. Berrin Tansel. Dr. Tansel is a professor of civil and environmental engineering at the Florida International University, Miami. She is a fellow of the American Society of Civil Engineers, a fellow of the Environmental Water Resources Institute of the ASCE, fellow of the Water Environment Federation. She is an eminent civil and environmental engineer, and we expect to gain a lot from her presentation. Over to Dr. Berrin Tansel for her presentation.
Thank you, Colonel Bhaskar. My talk is about advanced water treatment technologies and suitability for specific water applications. I am a professor at Florida International University in Miami, Florida. As Colonel introduced, I belong to several societies, and I'm chairing a committee, technical committee with the American Society of Civil Engineers on water reuse, desalination and water reuse. I want to acknowledge first SmartWWW Wastewater World magazine for organizing this webinar and the outstanding lineup of speakers that are I'm in the company of. I'm honored to be part of this group. My talk is going to cover what has changed in water demand over time and what new technologies are coming into the market. And I will summarize at the end some of the technological advancements and the state we are in. First, driving forces for engineering practice include breakthroughs in technology, demographics, challenges, economic and societal forces. Currently, we are in the middle of a challenge, of course, the pandemic. So that is going to result in some new technology developments as we are seeing in the vaccine, as well as some other effects in the technology. Over time, historically, there has been 4 industrial revolutions that has changed how we live our lives and how we use technology. The first industrial revolution is mechanical, which created steam, use of steam power, and how it is used in different applications. The second industrial revolution is electrical for mass production. The third one is more recent in 1969, the internet, which has changed our lives. And the last one that started in about 2000 or so is the use of cyberspace, the digital revolution. This slide shows the increase in population and the place in time of each of these industrial revolutions. As you can see, the population has been increasing in the recent years as these revolutions are happening exponentially. And we have seen significant use of technology, flights, airplanes, computer, internet, Wi-Fi. Of course, now the self-driving cars, they are coming to the market. So as the world population and technology are changing, the first 3 revolutions have changed the corporations, from an economic perspective. The last revolution, the digital revolution, has empowered people. So as a result, there has been some changes in how we live our lives. I'm going to look at the last revolution, the internet, which has changed from an environmental perspective as internet came into our lives. From an environmental perspective only, urbanization, we see urbanization, which has an effect. And later in the first decade of the 2000, with the urbanization, we see water shortage. We did not really talk much about water shortage before, but now we're talking about water shortage as an exponentially increasing challenge. So this, in 2020s, we have seen multiple challenges, pandemic, of course. We have seen some epidemics. We have seen the bird flu, swine flu. Urbanization has been increasing exponentially. And these challenges are going to be present as time goes on. About 20 years ago or so, National Academy of Engineering has identified in the United States and globally 14 grand challenges of the 21st century. These are engineering challenges that covers all engineering disciplines. Here we see the access to clean water. We also see the restoring and improving urban infrastructure, which includes the delivery of water to people. Environmental challenges, if we just focus on the environmental challenges, water is here in two areas. We are seeing freshwater shortage worldwide. It's not just a regional problem. We are also seeing as an environmental challenge food production from agricultural perspective, which requires water. So water is an interesting commodity, and it is becoming very valuable as time goes on. This shows water use per capita, daily water use. US is of course #1 here with over almost 600 liters per day per capita. India is about at the quarter rate, about 150 liters per capita per day. It doesn't seem as much, but if you look at the availability of renewable water resources, in North America, the renewable water resources include rivers and groundwater. In North America, there's a little bit more renewable water resource in comparison to Southeast Asia or South Asia. The next one shows renewable freshwater resources per capita. Brazil is declining. This is due to increase in population as well. It's the water as commodity is not decreasing, but population is increasing. So per capita availability of water is declining. If you look at US is here at the bottom on top, and then India is also here at the lower end. It seems like over the years, renewable freshwater resources per capita is slightly declining. This is mainly, as I have indicated, significant increase, exponential increase in population. We call this increase in population super exponential because exponential we usually use as first order, which has a half-life. If you look at these increments every 10 years, population is not increasing steadily. It is increasing a lot more. It doesn't have a fixed half-life or doubling rate. Water withdrawals per capita, this is the US, has declined in recent decades because of the significant push both regionally and also federally to recycle or reuse water. In India, it is fairly steady per capita water withdrawal, and also in China, it is fairly steady. The next slide highlights the need for agricultural and industrial water. Here in US and also Central and South Asia, we are seeing significant amounts of water withdrawal for agricultural uses. And also on the right-hand side, we are seeing for industrial use, North America, here Brazil, here Soviet Union and China and India has significant industrial water demand. This slide shows the water scarcity over the world. In 1995, we only seen some North Africa and some Middle Eastern countries here with water scarcity. But in 2025, which is not too far, only 4 years away, we will be experiencing water scarcity, if not already, in most of the world, most of the civilized world, will be facing significant water shortage. So the only solution right now, perhaps to reuse, recycle some of the potable water, because population is increasing and we have very limited amount of fresh water, and we need to be able to recycle and reuse some of the available water, most of the available water, which does not require high quality of water. These applications could include irrigation for agriculture. These are still, they require some treatment, but not to the level of drinking water. Irrigation and landscape purposes. Some municipal water supply, which could be used for applications which may not require drinking water quality. Also for industrial applications, indoor uses for floor cleaning and toilet flushing, dust control for concrete mixing and construction, supplying artificial lakes and inland and coastal aquifers, because nature has ability to treat. Even though we do not treat to the drinking water quality, nature can continue the treatment process, and for environmental restoration. Next, I will address some of the advanced treatment technologies which are becoming popular. There is some confusion in the term advanced treatment. For wastewater, advanced treatment, as I will explain in the next slide, it refers to technologies after secondary treatment. In water treatment, when we say advanced treatment, it means unconventional or new. It is something which is slightly different from what used to be unconventional. So regardless of the definition, advanced water treatment requires the water before the advanced treatment needs to be treated to some point. So for wastewater, as I mentioned, we have the primary treatment, secondary treatment, and anything after secondary, anything after biological treatment. This could be another biological treatment, physical separation, or some chemical separation. Anything after this is considered advanced treatment. For the advanced wastewater technologies, in some literature, people still say emerging, but these technologies have already emerged. They are already in use, but the terminology is emerging is still being used as it is being transferred, as the technology is transferred to other parts of the world. So I will cover briefly membrane technologies and advanced oxidation processes because they have certain advantages. Membrane technologies involves a physical separation, filtering water, using different types of permeability membranes. As you increase the pore size, reverse osmosis produces drinking water quality. Microfiltration does not produce drinking water quality, but it doesn't remove most of the contaminants. So to remove divalent like calcium, magnesium, we need to go all the way to nanofiltration. Membrane technologies have certain advantages. Currently on the market, we have two types of membranes: composite flexible membranes and ceramic membranes. And depending on what type of membrane is used, they can be oriented either horizontally or vertically. And these are very modular system, very small footprint, easy to use, and easy to have a secure operation. The next slide, this slide shows that a membrane process produces two types of streams. One is the permeate, which would be the treated water. The second is the concentrate, which contains whatever is removed from the water during the treatment process. And these include, the discharge of the concentrate includes mostly discharging to oceans or land application, which could be considered as a reuse. This, I want to highlight a few things. This is, of course, the drinking water treatment, and nanofiltration is close to drinking water usually is before the RO process, reverse osmosis process. It contains high levels of ions and salts. It is not typically suitable for agricultural use. And if it is used for agriculture purposes, the concentrate, this is the concentrate that contains all the material that's removed from water, it usually requires some kind of blending with fresh water. I also want to address as advanced treatment for wastewater treatment. This is on the wastewater side, a modular membrane bioreactor system, which replaces activated sludge. But these can also be used for remote applications, such as like toilet flushing and also for other purposes. And the advantage of this process is a standalone system. And a typical wastewater process requires secondary treatment. And this will replace, membrane bioreactor replaces these two units with much smaller footprint. The next, I'm going to briefly address advanced oxidation processes. These involve a chemical process, and they are classified by the type of chemical and catalyst used. We have 5 types of advanced oxidation processes: ozone-based, UV-based, electrochemical, catalytic, and physical advanced oxidation processes. Among these two, ozone and UV-based, are more commonly used, and we are seeing some of these newer advanced oxidation processes, phantom and UV oxidation. Advanced oxidation has certain advantages. It is fairly fast process because it's a chemical process. It breaks down the organic compounds. However, there are some challenges associated with advanced oxidation for operating cost and sustainability issues and general feasibility. Advanced oxidation requires an oxidant. It could be ozone, peroxide, chloride, or chlorine, a catalyst, and an organic compound. It requires 3. It is only targeting organic compounds. And they are compared in terms of electrical energy per order, which is defined as the electrical energy needed to degrade the contaminant. It's usually a carbon-containing contaminant by order of magnitude in 1 cubic meter of water. Of course, the top ones here, ozone and UV, are relatively cheaper. And examples of ozone advanced oxidation process, one example is this ozone, which is the most commonly used, and it can be enhanced by using peroxide, UV, and some catalyzed. The process can be faster and more rapid. One challenge, especially in the case of chlorine and some of the oxidants, is byproduct formation or product formation, which may not be completely oxidized. In the case of chlorine oxidation, for example, we have, of course, carcinogenic compounds such as total organic halides and trihalomethanes and haloacetic acids, and some inorganic byproducts as a result of oxidation reaction. Of course, which each advanced oxidation, the process is started by the oxidant, which creates a radical compound, which starts oxidizing different compounds as the time goes on. One main advantage of advanced oxidation process is that it is able to decompose some of the highly resistant compounds to biodegradation. So by chemical processes, we can degrade some of the pharmaceutical compounds and some of the inorganic micro pollutants. Well, I'm sorry, I'm going real fast for the time, but in conclusion, I want to highlight a few things. Water demand is increasing at global scale because population is increasing, and per capita availability of water is declining rapidly. Fresh water is in short supply, especially for agricultural use and industrial use, which has a high increasing demand. We will need to come up with some other alternatives for water reuse and recycling. We need to increase water reuse. Especially for non-potable reuse applications, we can have some water blending or some water reuse that could be suitable for specific applications. And we also need some advancements in water treatment technologies, and we also need to transfer some of the reuse technologies at the global scale to increase water reuse. That's my presentation, and thank you for joining this today, morning or evening, depending on your location. And I also, again, appreciate appreciate the Smart Water Wastewater for organizing this webinar today. Thank you, Dr. Tatwawadi.
Thank you, Dr. Berrin, for your nice presentation. We have a couple of questions for you. The first being about the most talked about, topic and theme, with water being a tradable commodity now on your New York Stock Exchange. Where do you see the futures will lead once desalination becomes a micro industry?
Well, we are seeing water becoming a major player in the economic market. It is getting to the level of oil almost in the future. You know, where oil is, water availability of water is becoming very short, scarce, and this is creating a lot of small businesses marketing water treatment technologies. We have seen it, especially for emergency applications after disasters. There's a lot of portable units that are being rolled out to specific locations. And I think the water will, over time, as the population increases, will be a commodity at the level of oil, in my opinion.
Thank you. The next one is about one of the graphs shown in your presentation about the water uptake going down. And does it mean that the farming based on irrigation in the United States is also getting affected? And if yes, how?
It was, yes.
It is a reduction in the uptake.
Yes, it was this slide. Here,
Yes.
this is declining. The reason for this decline is population is increasing. We have this sufficient fixed amount of water. As the population is increasing, this is per capita. Per capita availability is declining. Farming also has declined significantly.
Right.
However, now there is some push from the government to increase agricultural activities. There are a number of incentives because all the people, majority of the people are moving to urban areas, and these people need food, and the food will come from farming industry. So there's quite a bit of incentive to revitalize farming and to stop urbanization in the US.
Thank you, Dr. Berrin. I will now call upon Dr. Pradeep Kalbar. Dr. Pradeep is an assistant professor at the Center for Urban Science and Engineering of the Indian Institute of Technology, IIT Powai, Bombay. Dr. Pradeep will be talking to us on enabling wastewater reuse using circular economy, the challenges and opportunities in India. Over to Dr. Pradeep.
Thank you. I'll share my screen. Yeah. So thank you, Colonel Tatwawadi, for the introduction, and thank you, Smart Water and Wastewater World, for giving this opportunity to present this particular presentation with very esteemed panelists like Professor Tansel, Professor Rao, and Colonel Tatwawadi. So basically, I'm going to talk more of how we can use whatever the technologies. Professor Tansel has very nicely presented the technology scenario. I'll be speaking more from enabling this particular circular economy in urban water, and particularly in the context of India, what is happening in the field and how we can really leverage this opportunity of circular economy and make this particular circular economy work. So to further introduce my work, I work in these 4 particular areas. I call this 4 hats. So many people know me for water supply. People know me for wastewater management. I work in climate change mitigation and sustainability assessment. And I am core faculty at Center for Urban Science and Engineering at IIT Bombay. And we have a virtual center interdisciplinary program in climate studies, because climate is a very interdisciplinary topic and many things are there. So we have a virtual group also. So today I'm going to focus more on a wastewater story, which is a theme of this particular webinar. So specifically urban water cycle in India, if you see, we have to reach to circular urban water cycle. But currently we abstract water, we treat, we distribute, we consume, we generate wastewater and try to treat and then dispose. And there is no circularity. We are most in linear use of it. So this is our water cycle, but a lot of urbanization impacts are happening, which are like population, as Professor Tansel has highlighted, the population and other industrial uses are increasing, lifestyles are changing. So many issues are there. And changing from linear to circular is a big challenge. And we will see what are the challenges and opportunity into it. So we want to achieve this particular 6 R's. So entire presentation will be attached to this particular reduce, reclaim, recycle, restore, recover, these 6 principles of recycling. And there can be more R's also. People have listed many types of R. So particularly in India, the sewage treatment and generation scenario, if you see, every state is falling the gap. There is a gap between how much sewage is generated and installed capacity. So every city is behind installing more treatment capacity. And this is the overall in India, about 37 sewage treatment capacity is there. And rest is the gap. But we have to understand what is the important resource, but generated wastewater itself is a more important resource. And that particular change of mindset is needed. Recently this data was released again from Central Pollution Control Board. If you see, although we are saying we are in a gap of the treatment system, but if you see the capacity that is utilized, that is not fully utilized. So many locations I have found that treatment plant is there, but the collection system is not complete or not there at all. And the treatment plant is there. So we are in this particular situation where treatment plant of peak capacity for the next 30 years is installed. But I think we, as a consultant or as an engineer, we understand there can be modular construction, there can be phase-wise construction, but urban local bodies wants to go for a single tender for a 30 years contract. So there are so many issues, and the entire investment of huge infrastructure is going waste. So capacity utilization has to be focused, even if with the simple analysis. And so a couple of students are going to work on further detailing on this particular capacity utilization. But that I see a big gap. Coming to the quality standards, historically we have been used this particular general discharge standard of discharge, where our typical BOD in our mindset is 30, and there has been a lot of pressure to change and modify more stringent norms. So recently there was a change. I'll come to that. But if you see, these are the desired water quality standards for recycling, for toilet flushing, landscape irrigation, and fire protection. And you can see in Mumbai, the standards are there. Means in high-rise building committee has recommended these standards, more stringent than Western countries. Issue is enforcement. Issue is why and who will do this? That is the more important question to be asked. So it is not a question of whether we have a standard or whether we need a more debate on this. We have standard, and that is also recently given a clear order from National Green Tribunal that if your typical inlet is this sewage, the committee recommended these standards. Basically, for mega and metropolitan cities, 10 milligram per liter BOD standard, class 1, and other there is some still flexibility. But NGT has clearly said that all are equal and all water resources are equal, and we have to go for this particular aim for this particular discharge standard. Now, this poses a big burden on the infrastructure, because how cities will generate the money and how they can basically cope up with this particular new discharge standard, because they are already running to match 30 milligram per liter sewage treatment infrastructure. Now, suddenly 10 milligram per liter is a big challenge, but it can be converted to opportunity, and that's what I'm going to discuss. These are the broad approaches of wastewater management, and Professor Tansel has already given you the overview. But this is the management side, that we have to work on prevention also and conservation also. That keep neglected always, and we directly jump on treatment side. But this is a big box, big opportunities there. And we have to then move from treatment to recycling to recovery. And it's a big change in the infrastructure mindset and infrastructure planners that has to be brought in, that it's not only the treatment, but we have to lead to a recovery. And then there is a building level treatment, then there is a decentralized, and there is a centralized. So this spectrum also we have to keep in mind. And there are different technologies from physicochemical to biological, aerobic to anaerobic. There are suspended growth and attached growth. Everyone, I think the people in water industry know this particular diagram. So we have the technology, we have the need. So what's wrong? Why we are not able to achieve this? That is the bigger question. So what is wrong with the current approach? So if you see, this is, let's say, physical boundary of the city. And what we are doing is we are having the agriculture land which is using artificial fertilizers to produce our food. That food gets consumed in the households. We use detergents and chemicals in the households. We fetch fresh water from a large dam, stored water hundreds of kilometers, for example, in Mumbai city. And then we generate wastewater, which is again having this NPK and organic matter as a pollutant. And then we have a centralized treatment system, which is discharging this sludge and the effluent. And these all carry all these particular nutrients and energy. So issue is that on one side, we are fixing the nitrogen at a huge amount of energy in the industry, in the fertilizer industry. And we are again putting the energy back to release this nitrogen back to the atmosphere. So you can see hello. Yeah. So you can see on one side, you have a huge investment on the energy for fixation and then release. So this needs to be fixed. We have to stop this particular use of artificial fertilizers and create the fertilizers from this sludge. And that is a huge technological change. A lot of policy changes need to be done. We have to stop consuming the fresh water as much as possible, and we have to create the secondary uses of the water that we are already fetching. So virgin water consumption has to be reduced, and we have to stop consuming the energy. We have to make our treatment system as energy neutral as possible, and we have to create the energy also from this particular system. And this will happen if we plan and change the policies as well. It's not the technology, but policy changes are also required. So this will happen only if we apply decentralized, because if you put everything at a very far end of the system, decentralization is the only solution we can achieve this. And when I say decentralization, many people get upset. People say, oh, why decentralization? Do you know what is the problem? I know, I worked in industry. I know what are the problems and issues with the technologies. So the issues here are, we will discuss in the decentralized and centralized later, but consumer awareness is another big challenge. So basically, centralized system, as we all know, it is a tail end system where everything is taken out of the city boundary or towards the end of the city and then treated. In decentralized, we try to do some scalable small scale systems where decentralized treatment can be used. Now, the issue is this decentralization is of the scale. Two small systems difficult to operate and govern and do not offer scale of economy. So we have to do not jump on a decentralization just blindly. We have to also need to look at the what is the scale of economy, how small systems are feasible. So and highly centralized systems place a challenge in recycling of treated effluent and sludge, because if you put everything at one place and try to recycle, again secondary distribution network cost will become, sludge transportation cost will come, and there is no scale of economy beyond one point. So all engineers will understand this, that this, so the scale of economy is somewhere in between. So, and this additionally requires deeper sewage network for flat terrains and difficult to maintain. So I've seen in many cities the situation of sewage network. Enthusiastically people go for a sewage network underground, and then maintenance is with the urban local body. It is very difficult to manage for them. So we have a spectrum from highly centralized to highly decentralized to highly centralized. The currently urban local bodies, and I would say consultants, are also very comfortable with the this particular idea of highly centralized infrastructure. They are trained, that they are basically trained to think in that manner only. And I request all of you take an, because see, it is easy to prepare DPR in one shot of a centralized system, propose everything in one go and just go for a big budget project. That's everyone likes. Politicians, consultants, EPC contractors, everyone likes that. And that is, I see as a very big problem we have, and a lot of changes are there. Coming to decentralized, people originally put very small systems at building level, and somewhere which is not feasible, the building societies are not interested to operate these treatment plants. So who will take care? Because so we are at this one far end and another far end. The ideal zone for implementation is this in between, where this, for every city this scale will be different. So we have to identify for that given city how we can segregate the centralized system and have a decentralized system, so that the 6R, that is recycle, reuse, reduce, all those will be implemented. If we have that kind of flexible infrastructure, that it will create a much more opportunities than a centralized infrastructure. That's the whole point I'm trying to make. So the challenges in wastewater recycling is scale of implementation is not known. People just go for a centralized, that because there is no knowledge. So we are working on that to create that knowledge. Energy requirement, can we make it energy neutral? Because there is no revenue with the urban local body to operate these plants. So much of dark situation, people put off the aerators because they cannot pay energy charges. So this entire infrastructure will go waste. There are resources to be extracted, nitrogen, phosphorus, lot of technology scale up is needed. Pathogens and pathogens removal. If you want to recycle water for higher ends, there's a question of reliability, because we have to develop a system which is reliable. If there are risks posed by the treated wastewater, so whenever somebody asks me why you say that costs are higher, because I'm imagining a very reliable system. Because if you say we'll provide you recycled water to industry, you have to provide. You cannot say tomorrow, okay, today my plant is not running, or today this particular parameter is not working. So that reliability cost also need to be incorporated in the system. That's why the cost of recycling water has to be properly counted. Emerging contaminants, we are already not able to match the carbon, BOD, nitrogen, phosphorus limit, and already so much use of household chemicals. And that's why I said consumer awareness. So many chemicals are used unnecessarily in the households and getting discharged, and that is posing another challenge to the recycling of water. Revenue models, who will fund this capital infrastructure and operation maintenance? That is a big question. Operation and maintenance, capacity with the urban local body, skill manpower, governance, and conservation. So these all need to be thought of together to really imagine this particular system. So we have basically, I have documented this entire story in this particular paper. You can read here or write to me. I will send a copy. So basically what we are saying is we have this particular urban water cycle where water treatment plant, urban area wastewater treatment plant is there. And currently we are doing it in a linear way, that we are disposing of the water and the nutrient. We have to go for implementing these 6 R's, how we can change this picture from going the next city, so one city passing on the problem to another city, how we can fix this is the entire effort that we need to pose. So basically what we are, first we have defined what is recycle, reuse, and those definitions needs to be clear. So reduce, everyone at every phase, we have to reduce the water wastage and consumption. Reuse, cascading of the resources, without treatment, how much water we can use. Recycle, city using its own water for the secondary purposes after treatment is recycle. Reclaim, city selling water to industry or industry buying water from city or some other stakeholders is a reclamation. Restore, when there is no enough buyers. In many projects I have seen the good treated water is available, but there are no enough buyers. There is a policy gap. So you can again recharge the groundwater and recover. So energy recovery, nutrient recovery is the next phase of technologies that we need to adapt. So basically, circular economy provides you this kind of particularly very nice framework for the bureaucrats and the managers, because here you apply system thinking, volume optimization, innovation, collaboration, stewardship, and transparency. We have identified how urban local bodies can work with industry and do this particular mapping of each of their R's with these particular principles of circular economy. You can go through this particular detail, very thoughtful. My PhD students have, and I have worked on and given this particular tabular formulation. So how we can apply system thinking, value optimization, innovation, collaboration, and stewardship and transparency. So that is the framework we have proposed. So what an entire point I'm trying to make is that cities first need to create a market for recycled water, because if there is no market, there is no point in putting so much of infrastructure. Only there will be regulation. But by meeting a regulation, if you can sell, the sustenance of the system will be improved. For example, let us discuss the Mumbai's case, where city of Mumbai, as if you all know, it is a coastal city. It's an island city, and these particular locations 1, 2, 3, 4, 5, 6. So there are 7 locations which are the draining point of the city, and this sewage flow is given here. So now city's planning, current plan is that they want to go for sewage treatment and recycling, because there is now this NGT order. So to achieve the high effluent water quality standards, the MCGM plans to spend around 20,000 crores of its on its 7 sewage treatment plant. So if you make such investment, it also demands that you must follow with efforts to utilize the huge volume of recycled water. So you can imagine 20,000 going in just for treatment is not a complete utilization. Why recycling is not possible in current context? Because it is not known who will consume the treated sewage unless there is a market for it. Cost of recycled water is around 10 to 12. It is not accounting the distribution cost. It is just the treatment cost I'm talking about. Whereas the freshwater tariff is about 3 to 6 meter cube per 3 to 6 per meter cube. So there is a significant variation at a regional level. So although the MCGM has a telescopic billing policy, but the connections are not metered, not mapped. Most of the meters are dysfunctional. So the implementation of telescopic billing policy remains on paper only. So the production cost of water in Mumbai is about ₹15. So it's the issue of the price. At what price we are producing the fresh water? The revenue of the demand and collection from the MCGM is same for last entire decade. Okay, so basically there is no change in the raising the bills. That is the scenario currently. So this shows that the gap between production cost and revenue remains unbreached. And the MCGM, even in the DPRs, it is written, the plan is to have 25 to 50% of recycling at each recycling station. Let's say even the 10% realistically we plan, it is about 400 mld. The big question is who will be ready to use it, who will distribute it. It's a big question. The next issue is the location. The planned recycling stations are highly centralized at the fag end of the system in the near coastal areas. It will need a large secondary distribution network in mostly concretized roads already crammed with dozens of the other utilities. So instead, decentralized recycling station of about 50 mld. Now this 50 mld is my number, means you can debate about it, but for city like Mumbai, 50 mld also can be called as decentralized, and maybe more feasible in Mumbai case, as this will create an opportunity for establishing localized recycling network. And this, as I said, this number has to be decided for each city. For 100 mld kind of sewage flow in a city like Kolhapur, the decentralized scale will be different. So buildings can then have a second water connection from such localized recycling water. and modification in the storage and internal distribution. So there are a lot of changes in the consumers infrastructure are needed. The guidelines and bylaws, because the existing bylaws do not anticipate other water resources for non-potable use. That needs drastic change. So it's not the technology, it's not the physical infrastructure. So bylaws need to change to enable mandatory dual plumbing system for future buildings. I know it is difficult for existing building, but if we do not act now, it will be too much late. Again, 10 years, I'll be making the same presentation that there is need for dual plumbing system. There is no point. So resizing of all the municipal connections, because current connection sizes are huge in Mumbai, at least we know. So residential, commercial, industrial established to restrict potable water supply for domestic purpose only, because they are getting a benefit of fresh water. When if you change the connection sizes, or you cut off the connections, some stringent action has to be taken. And mandatory uses for efficient water fixtures, and if possible, a rebate, associated rebate, and minimum physical losses in the distribution system. That is another story, how we can improve water supply. So creation of a recycling market will happen when the urban local bodies will work and talk to institutions, commercial establishment, industries, railways, metro boards, port trust. Small soil treatment system need to be created by working with these stakeholders, and we need some enablers. And I'll be happy to collaborate with whoever to work on this idea. And there is a need to provide comprehensive procedures and guidelines, responsibility of each stakeholder, who will sell, who will buy, at what cost, the level of treatment required, its use after treatment, expenditure. All this needs to be defined before we jump for a very fancy high-end recycling stations. So in summary, there is no immediate need for toilet to tap. Many people go abroad, see that, okay, everything is connected to, that is fine. In Western countries, we have, I told, the reliability, the guidelines and everything is there. So enough other avenues are available in India for other secondary purpose. We have to first create a practice of recycling of water. Recycling at the point of use or sale, that is the key. That if you recycle at some moon on Mars, who will distribute that water? So that is another challenge. So it is necessary to change existing guidelines and bylaws. Scale of implementation of the solution is important than the solution itself. Many people spend time on technology discussions, but what is the scale you are implementing? That is more important. A recycling water market need to be created in hand with recycling station, because unless you have a market, there is no financial sustainability for these recycling stations. Decentralization and closing the water, carbon, nitrogen, phosphorus and energy loops is the key to achieve the sustainable infrastructure. So I think that's all what I wanted to share from my side as far as my understanding about this topic, and I'm really happy to be here with this particular group of esteemed members. Thank you.
Thank you, Dr. Pradeep, for your very insightful presentation on the circular economy insofar as it relates to the water reclamation and reuse. I have a question. If we are talking about circular economy, we need to close all the loops, be they local, national, or regional. Now, I agree entirely that we need to create a market. We need to do the market survey for the recycled or reclaimed water. But the issue is, where do we start? It is an egg and chicken situation. Unless we go for projects which are for reclamation of water, there will be no thinking about creation of an infrastructure network for its use and distribution. So what I feel is that both of these should go hand in hand. And as you know, any project for reclamation from concept to commissioning may take about 3 to 5 years, which period I consider is good enough to create and generate a market, and then also provide the necessary infrastructure starting from a small scale to the intended scale. And you can always scale up and also find out and get some innovative solutions, some of them being use of this reclaimed water for construction purposes and creation of infrastructure itself. Thank you very much for your nice presentation. There are a few questions which our audience has. One of them is, about transportation of water to areas which are drought prone from the areas which have plenty of water, and the transportation method has been suggested as barges. What do you have to say about transportation of water to drought prone areas?
Through barges.
Any mode of transportation, I would say.
No, there are some grid schemes happening, like Gujarat has a grid, pipe grid, Marathwada is coming up with the pipe grid system. But from barges, I don't have any experience on the barges side. Definitely.
There is another question about can we have, or can all the human beings have clean water by say 2025, and clean water is a basic human right.
Yeah, means the rights and sustainable development goals are there. Issue is how we'll achieve this. Means 2025 is a very small time frame, at least in India, I would say, frankly. We don't have to give some false hope. There are so many issues. We have recently conducted a study in 10 slums in Mumbai, where the issue of water access and sanitation was studied, and situation is very dark. There, even if there is a water, people have political issues and other issues to supply water. So I don't see immediately that is happening. It's a big challenge and big battle. I don't say that urban local bodies are not working. They are working. Whenever I meet the engineers and they have their own challenges. Our society, our economics, our political ecology, everything is different. Making one change is very, it needs three key people. One is the topmost bureaucrat, a topmost technical person, and the minister or the in charge, whoever. These all three people has to be like-minded to bring that change in the solution. And I see, when I talk to a very good technical chief, the bureaucrat may not be interested. When I talk to a very good minister, other two people may not be interested. So the ideas will go vanished, and the transfers and all these dynamics, our governance.
Thank you. The next one is for Dr. Berrin Tansel. Could you unmute yourself, please, madam?
Sure.
Yeah, thank you. This is about a question on the membranes. So what are the recent advances in the membranes for wastewater treatment, and what is the life in use of these membranes?
Yes, the life of membranes is, we consider indefinitely, but nothing is indefinite. Membranes foul depending on the use conditions. And in the US, the recommended for drinking water treatment, the recommended lifetime is about 5 years. They need to be replaced every 5 years, but I have seen drinking water facilities using them for 10 years if it is still working, not fouled. In terms of new advancements in membranes, since the fouling is a major problem for membrane technologies, now I'm seeing these vibrating membranes to reduce fouling. And also, of course, these are flat membranes, not the rolled membranes. And also some membranes that allow backwash, and ceramic membranes, which allow, if you heat it, you can heat the ceramic membranes and you can regenerate some of the membrane capacity. So those are some new advancements we are seeing.
Thank you. The next one is for Dr. Srinivas Rao. Dr. Rao, could you unmute yourself, please?
I didn't even present yet. Okay.
Good. You can always take
That's
a
fine.
question. Okay. This is about the recent reports that due to the wildfires in California region, several water lines, which were, plastic based, PVC or HDPE, they got damaged, and the supplies coming through these lines, they are contaminated with benzene. What, in your opinion, would be a better material to avoid this kind of situation in the future?
Well, the buried or underground infrastructure, we are using the PVC pipes or the ductile iron pipes. So, where the wildfires, naturally caused or for other reasons, uh, it goes back to the how we design the buried infrastructure and the type of material. Again, there is that engineering code and how we have this decentralized facilities or the protection from fires and other situations. So every material is a material of construction. You take any kind of pipe, but the main the core is the type of material, and when that decomposes or due to these fires and other situations, those the leaching of those chemicals or the makeup of those materials. So that's how much I can look into. That's a serious situation. Good question.
Another question related to this is the wildfires and such like extreme events are now happening, and therein comes the element of resilience to the climate change and the climate change episodes, like wildfires, extreme rainfall events. Is there any proposal or is there any reference of the stormwater, wastewater, and water being taken as one entity in any utility for water management in the United States?
Question to me?
Yes, sir.
Yeah, sure. Well, the existing wastewater treatment facilities in the US, now we address them as water resource recovery facilities. And the influence we have to take care of is include not only the sewage from the residential, the human waste, but we have to handle leachate from landfills, the I&I, inflow and infiltration, the wet weather flows, and pre-treated industrial wastewaters. So the existing wastewater treatment facilities, we already do that. And but the infrastructure needed in the collection systems. For example, if major cities going for the tunnel-based storage, where you are looking at a billion plus dollar investments. So, but again, end of the day, the wastewater treatment has to happen and meet the effluent quality parameters as per regulatory requirements. So, hope I answered that question.
Thank you. Thank you for your answer. We now move on to our next presentation. And by coincidence, the presenter is Dr. Srinivas Rao. He's an independent consultant from Ohio in the USA. He's also an adjunct professor, Central State University, Ohio, in the Water Resources Management Department. He's a member of the American Society of Civil Engineers and a past chair of the Committee for Advanced Technology, Advanced Renewable Energy Technologies Committee. Dr. Rao, we are eager for your presentation, sir. Over to you.
Thank you, Colonel Bhaskar. Let me set up my presentation real quick. I think first I have to, share the screen.
Let's make it full screen.
Oh, make it full screen.
Yeah.
Well, I'm going to put in the presentation mode here. Is that good?
Yes, sir.
Yep, thank you. Thank you, Colonel Bhaskar, for the introduction. And welcome and thank you for your time listening to us. And it's I'm thankful to speak along with the experts here today. And thank you all for your time. Well, now the professors has said, the high-level classes, right? So now let's all,
Screen is freeze.
deal with the homework assignments. See if we can solve these, those complex questions and get better grades, better than a B grade, right? We'll certainly try for an A. So let's do that. So I'm going to, speak on the little deep dive on, what are the treated municipal wastewater and what are the goals and what are we accomplishing, and direct potable reuse. Yeah, we want to accomplish on that. So I like the logo created by the Smart Water and Waste group, and really, this is what we see when you are in the field: the drinking water systems, wastewater systems, and what we don't see is all that buried pipe infrastructure, miles and miles. Just imagine the treated drinking water has to be supplied to all over the places in the city, and how many miles that would run in the distribution systems. And similarly, we need to collect all that used water, and the collection system, how many miles that would go. So the daily operations on municipal water infrastructure is really, if one imagines how things go 24/7 basis, amazing. With that, we are going to briefly take a look at, again, mostly all this information I'm going to present is with respect to the USA, United States. And so we'll touch on the water wastewater infrastructure, and then the applicable, the drinking water standards, and then treating the municipal wastewater, and what is that quality we are accomplishing, and how that looks like. And as professors provided more information on advanced water treatment systems, we'll briefly look into that. And then the waste, the municipal water systems, what's the energy needs are, and where we stand on that, and what's about the, similarly on the costs. So then we'll touch on the legislation and regulations in the US, and I will have some summary based on the presentation. American Society of Civil Engineers, they do a infrastructure report card every 4 years. So the next one is coming up by end of March. So we are just using this old one, and it has the critical information we have been dealing with all along for the last 4 years. And I want to briefly touch on 3 things: the drinking water processing in the US. So as per the report card, there is a water loss, drinking water, the processed, the potable water, we have a loss of 6 billion gallons. That's in approximately 23 billion liters that is lost every day in the US. And then the wastewater processing demand is supposed to grow by more than 20% by year 2032. So there is that ongoing demand for wastewater processing. And the energy, there were more than 3,500 power outages in a year. So we need the water systems operating 24/7, and then that energy piece is critical, right? So before we get into the our drinking water, wastewater, so where do we fit in the big picture? So for example, imagine the Great Lakes watershed or the Great Lakes Basin, and we have environmental contaminants, either point sources or non-point sources. And when we withdraw water from surface sources, surface water sources or groundwater resources, we draw the water, and then to make it potable, so we have applicable drinking water quality standards in every country, and we follow that. We need to follow those and provide that quality potable water. And all the spent wastewater used by the residential, commercial, institutional, industrial, or other agricultural uses. So the way we have to collect all that wastewater and then bring it to the water resource recovery facilities and then treat it to the applicable effluent quality standards and safely put that, or we have been putting that back into the watershed. So the way the watershed in the US, we are governing or the regulated utilizing the TMDLs, the total maximum daily loads. So that's how you see how the circular fashion of we are trying to maintain good watershed health and water quality. To give just an example, just I know we have audience from various countries, so this is just to imagine for India, if Ganga River Basin is the biggest, is the largest in India, then just apply and see the challenges what we are in maintaining the good watersheds. So this is again applies to any watershed anywhere in the world. So on the drinking water quality, because the sources could be surface water, groundwater, now we are talking about, or we have been talking about treated municipal wastewater effluents. So the small acronym there, TWWEs. So the source water, we have to watch out for the types of contaminants, physical, chemical, biological, radiological. So again, the professors touched on these acronyms: natural organic matter, NOM, total organic carbon, TOC, HABs, harmful algal blooms. And then when we are disinfecting water for the final quality, then we are faced with disinfection byproducts. So in the US, we have more than 50,000 community water systems or the public water systems. These terms are defined under the regulations. So we use treatment techniques and the treatment trains to get to the ultimate drinking water quality across the US. The drinking water quality standards in the US, we have primary drinking water regulations. They touch on all the categories of contaminants, and we call them MCLs, maximum contaminant levels. And US EPA, US Environmental Protection Agency, enforces those standards. So the public water systems have to meet day in, day out. There is no other way, and show that water quality. And there are secondary drinking water quality regulations, and they are to control the aesthetic, cosmetic, technical effects. I have provided those links, you can look them up. And US EPA does not enforce the secondary maximum contaminant levels, the SMCLs. And again, Code of Federal Regulations, that's where you find all these regulatory requirements. And bottled water is regulated by the Food and Drug Administration. So the CFR title is 21. The environment protection, it is title 40 CFR. So under the drinking water regulations, again, we receive the potable water day in, day out. So the public water systems have a regulatory requirement. They have to publish an annual report on the water quality that was supplied to all the consumers. And those reports have to be made available to all the consumers. So you can find them on the internet and find out the details. It's a good read, and how much effort goes in have to preparing those annual reports, and then you can see those numbers of all the water quality parameters, how the water was processed and the final water quality you have experienced. Now moving on to the wastewater treatment, EPA has the NPDES permitting, National Pollutant Discharge Elimination System. And the wastewater processing, the facilities have a regulatory requirement. They have to submit discharge monitoring reports, DMRs, every month to the state and federal agency. And good amount of this information is available in those databases. And it will show you the not only the quality the effluent quality information, you can also see any violations on the quality. To simply take a look at a schematic, what happens at the water resource recovery facilities. As I was saying, answering a question, the influence, you see the range of influence a wastewater treatment facility can experience. The sewage, septage, leachate from landfills, pre-treated industrial, and the wet weather flows. That's your rainfall runoffs as collected. And the one other thing is missing is the inflow and infiltration, I&I. So now, if these are the variety of flows are experienced by the system here, then how you are going to manage to get to the effluent quality here at this end. So that's where whether you call it is magic or logic, all the treatment that is included in the treatment train. And basically we look at two trains. One is for liquid train, the processing of liquids, and then once we separate the solids from the liquid, so that becomes the solid strain. So the two complex operations, and to get to that effluent quality, right? So they mostly the effluents are going to the watersheds. So a reuse is important, as our expert professors, and then the circular economy or the water availability into the future. So that reuse becomes critical. And again, everything happens by the regulatory requirements up to the quality the facilities have to achieve. So the solids, land application is the first preferred method. And we call them Class A solids, Class B solids in the US. 40 CFR Part 503 addresses these requirements. And if the solids are not suitable for land application, they go to a landfill, a regulated landfill. And if there is incineration that has to be done for the solids, then the ash has to go to the designated landfill, where that can be disposed of. So, the discussion, we continue on the effluent reuse. So the effluent quality parameters, again, we check on the physical, chemical, biological, radiological. So this is a list of a slew of these parameters, beginning from pH, temperature, BOD, COD, ammonia, nitrogen, total phosphorus, total dissolved solids, TDS, oil and grease. So we have various, the contaminant parameters, how we are accomplishing, when we say we are treating wastewater. So I have found some information from this reference, Water Reuse, a good book to read, published in 2007. You see these parameters, effluent quality parameters, and then this data is for, we generally use conventional activated sludge process or upgraded to biological nutrient removal, BNR, or the advanced technologies like using the membrane bioreactors. So these effluent quality parameters and the numbers you see here, the lowest side that we accomplish using a membrane bioreactor. And then, so again, we have more than 15,000 wastewater treatment facilities in the US, and not all of them are using membrane bioreactor. So anywhere, a type of activated sludge process, and with or without biological nutrient removal, given the geographical location and the applicability of regulations on the nitrogen and phosphorus. So we see these are the numbers we see for the effluent quality. So if this is the effluent quality, again, you see the turbidity less than 1 to 15 nephelometric turbidity units, and the total dissolved solids 500 to 700, and some numbers you may see more than 1,000 milligram per liter, and the surfactants, the organic materials. So moving on, again, on that list, we didn't see oil and grease. Oil and grease is also critical. And here we did a review back in 2019 for all 50 state capital cities, what their 2016 effluents looked like. And you see on the y-axis here on a log scale, see the oil and grease milligram per liter, it's significant. above 1 milligram per liter or the 10 milligram per liter. And again, the numbers, you see here, the data are the descriptive statistical numbers you see here. So basically saying oil and grease is important. And then Professor Tansel touched on membrane fouling. So, it's important to have that good handle on all the effluent quality parameters. Now, this is the DPR schematic. We have presented this in 2019. And basically what you are looking here is, the drinking water systems, from a raw water resource. This is a regulated entity. And then, the potable water product is, supplied to all the consumers being residential, commercial, institutional, and industrial, and some agricultural. Think about those livestock operations close to the cities or in the municipalities. So once the the wastewater is generated and collected and received and processed at the water resource recovery facilities, so mostly the clean effluents going to watersheds. That's where we want to draw and then apply this advanced water treatment. And again, what's the thought process here? Where we are at? Can we process to add it to the raw water as a raw water resource, or can we take it and add at some point within the treatment train, drinking water processing, or can we directly put it into the distribution system, or can it be supplied to a consumer? So these are the possibilities. So that's how advanced water treatment becomes critical, and that has to be a permitted operation. So the regulatory requirements and so on will be there. So advanced water treatment systems are explained by the professors, and so the preliminary treatment will be required based on that effluent, the clean effluent quality to remove the floating and suspended solids. Advanced treatment we can accomplish, and the RO, reverse osmosis, nanofiltration, and advanced adsorption systems. So there are many advanced technologies are available. And again, the treatment train will also include advanced oxidation processes, as explained by by Professor Tansel. So here we show some data for an advanced water treatment that is utilizing microfiltration, reverse osmosis, and ultraviolet advanced oxidation process train that completes the whole train. And then take a look at those individual parameters, turbidity less than 0.1 nephelometric turbidity units. In general, at a drinking water plant, you see the turbidity produced at less than 0.3 nephelometric turbidity units. So, these are all, regulated, and we have those drinking water quality regulations. So we have to meet those standards. So now, compare these numbers with those applicable drinking water quality standards, for individual countries, the cities, or as recommended by World Health Organization. And again, the stringent requirements. Again, the numbers they show, for total dissolved solids, less than 5 to 40 milligram per liter. In general, we experience anywhere from say 200 to 300 milligram per liter in general. But again, when you have high hardness water, you may see more than 400 milligram per liter. And any other additions of chemicals can also increase total dissolved solids. Chemicals, maybe I should say minerals, for the good quality of water. So, all the parameters must be verified. If not, shall be verified at the highest level. So, the energy requirements, right? It's important. We noted that. So in the US, and I presented some numbers here. These are not any benchmarks. Generally we observed this data, and then we utilize when we work with, the water systems in the US. So treatment and distribution system, you see that 0.8 kilowatt hour per cubic meter. Wastewater treatment, 0.7 kilowatt hour per cubic meter. And, there is a spatial average. We've seen how much US government, is coming across, spending on the energy from water intake to watershed return. So some number, this is a spatial average, 1.3 kilowatt hour per cubic meter. So again, energy use is facilities, specific. You can try benchmarks. There is a big effort going on, but benchmarks have to be apples to apple, right? And again, if it is a green apple and a red apple, we have to notice the difference as well. So that's how stringent you have to be going, if you are going to establish benchmarks. Now on the advanced water treatment, various water treatment trains, they're high technology processes, and then the energy requirement could be above 0.3 kilowatt hour per cubic meter, or 0.5 or higher. So that's the story on the energy need. In the US, parameters, we say is generally, around this 1.3 kilowatt hour per cubic meter, around say 5,000 kilowatt hours per million gallon water processed from water intake to watershed return. Now the costs. So we looked at the energy needs, and then the costs, costs again has to be with reference to water quality standards, right? That's where the final cost we have to estimate. So for the advanced treatment costs, the capital expenditure and operational expenditures, anywhere from 70 cents to a $2.21 per cubic meter of water, and then we have some number provided in gallons per 1,000 gallons. So these numbers for some little bit of data available for 5 mgd, in mgd being multiply that by 3.8 or so, so you'll get your liters per day. So these numbers here are we how close are we for the real numbers here? Are we off by some couple of log orders? For example, is it $2.21 or it's $200 per cubic meter? The advanced treatment or the high effluent quality treatment. So you have to deal with, how you are going to dispose of or operate the systems in completion. For example, if we generate those rejects at the advanced treatment, how they are going to be disposed of. So that's how you have to be good at, taking a look at the costs. And on the same token, as Professor Kalba talking about, put them things into circular economy. So you need to get to that positive cash flow. And then energy neutral. How are you going to accomplish energy neutral? Yeah, we have a lot of effort going on in the US and worldwide. And how you make your, at the least with the wastewater treatment systems, making them energy neutral. There is that possibility. And then bringing in renewables, the solar power, wind energy, and then, arranging that type of effective cash flow that is required to present to municipalities. So that effective evaluation on costs is critical. So on the legislation and regulation side, EPS, EPA has this information. Pardon me?
I said last 2 minutes.
Okay, thank you.
Yeah.
So, the state of California, DPR, the definition matches with what I have shown in that, DPR schematic. And, California Water Code also includes the advanced water treatment, should include all of the following: the microfiltration, the preliminary treatment, the advanced treatment, reverse osmosis, and advanced oxidation. And the product water, shall meet the federal, state drinking water standards. So a few other states, Texas, Arizona, they have DPR regulations in making, and there are real facilities operating in Texas and in California. So summarize, the wastewater effluents to DPR, it has to be well established. And the clean effluent quality is really critical, how we apply the advanced water treatment system. And we have to observe the federal and state water quality standards, the applicability, to the complete. And the energy requirements, costs are significant for the advanced water treatment systems. And the DPR, the permitting of the advanced water treatment systems would be required. And as we all heard, the operation of the municipal water infrastructure in the circular economy is necessary. With that, I thank you for your time listening to us, and I acknowledge Dr. Gullapalli, Professor Bill Ritter, and colleagues worked with me on the subject, and thank EWRIASCE for publishing our technical papers. And big thanks and appreciation to the Smart Water and Waste group. Thank you, and here to answer questions. Thank you all.
Thank you, Dr. Rao. Just one question about, your advice. How would you advise the developing countries in Africa and their regulatory agencies to adopt the effluent standards which you have mentioned from the United States? Or should they focus on building local technologies for wastewater treatment? Because in most cases, they import the technology but do not have the capacity or the required knowledge to run those plants after these are built, or the owners of capital do not understand the technology. So what do you think about this?
Yeah, good question, and what we have been facing. And we have a system in place, as designed, effectively designed by the engineers. And the operation of those facilities day in, day out is so critical to meet on the effluent quality. So the systems being, they could be small systems, like anywhere from the pond systems, the lagoons, to the advanced activated sludge processes with biological nutrient removal. I am also involved in the training of the workforce. So we need those certified water, wastewater operators. And in the US, we certify them anywhere from level 1 to level 4. And states like Massachusetts, they have up to level 6. So these are so well-trained operators, managing, taking care of these facilities day in, day out, and their interaction, bridging the gaps with the cities and with the engineers. So that's how collaborative it has to be. So hope I answered that question.
Thank you. Thank you very much. Would you kindly stop your share screen? Thank you, Dr. Rao.
Thank you.
So with that, I come to the last presentation. This is my presentation and the last one of this Indo-American webinar. The topic of my presentation today is the water reclamation and reuse, the India story. Now, every project, every water and wastewater project, it is conceptualized, it takes birth in a context. And here, I want to first discuss the context. What is the big picture in India? What are our compulsions to go for water reclamation? Based on these compulsions, how we have developed our concepts and philosophy for reclamation of water. I have my own idea of a modified water cycle. When we talk about reclamation, there are several issues which are related to all the stakeholders, and then there are policies which are generated out of all these issues. Once I have discussed this, I would like to discuss with you a few case studies of municipal wastewater reclamation and a few case studies of the industrial wastewater reclamation. Now, talking about the concept, you see, uh, there is this mission mode program of the government of India, that is the Jal Jeevan Mission. The program is Har Ghar Jal, water on tap for every household in the country. And this mission is being implemented by the government of India at a cost of 3.5 lakh crores. This capital outlay on the project will be available and the project will be implemented in mission mode in 5 years. About 172 million households which do not have water on tap in the country, in the rural areas, will be covered under this mission. The mission aims to provide safe drinking water to all these households. It was launched in December 2019 and is expected to be completed across the country by 2024 December. The important thing to remember here is that although we are going to provide 172 million households with water supply connections, households which at present do not have any water supply connection, the sources of water which existed in India so far are the sources which are going to provide water on tap to these households also. And therein lies the challenge. I want to talk a little bit about the climate change resilience. What has happened globally is that all the water systems, wastewater systems, other urban infrastructure, rural infrastructure, these projects have been conceived, have been designed and implemented without any regard to the climate change resilience. The result is that we are seeing today extreme climate events like wildfires, extreme floods, and our systems are clearly not designed to take into account the impact of these changes which are happening due to climate change and which are impacting our existing infrastructure. There are the agents of change, there are the systems, and there are the institutions. All the stakeholders involved in the creation and utilization of infrastructure, they are part of this social and economic activity. And to improve the well-being of the consumers, of the societies, communities, and the country, it is important that we bring in the elements of climate change resilience and incorporate it in the planning of all our future infra projects, including the projects related to water and wastewater management. Very important issue here is that during the last 70 years, the per capita water availability in the country, and I know Dr. Berrin also touched on this aspect. In India, the per capita water availability has reduced from over 5,000 kiloliters per person per year to less than 1,300 kiloliters per person per year as we are talking. This is the second major issue of my context. Coming to the third issue, as of last year, the urban areas where it was mapped were generating about 62,000 million liters per day of sewage. The treatment capacity, which is being augmented all over the country, is now capable of treating about 24,000 million liters of sewage per day, which leaves a deficit of about 38 to 39,000 million liters every day. This untreated sewage mostly finds its way in the rivers and other water bodies or groundwater, which are the sources of water supply to all the communities and which are going to supply water to all those 172 million households which I talked about. My context is also that the National Green Tribunal of India in 2019 upgraded and updated the discharge standards for treated effluents across the country without any regard to whether it is a metro city, a non-metro city, a village or a town or a small town or a small community. These are uniform discharge standards. Now, there may be differences of opinion about the implementation strategies of these discharge standards, but uniformity of standards is something which I personally welcome. And there is no denying the fact that because the standards have been revised, they have given a big boost to the recycle, reuse, and reclamation industry and the reclamation effort. Because what happens is, if we agree in principle that wastewater has to be treated and a cost has to be incurred on its treatment, then my argument is that with a marginal increase in this treatment cost, this wastewater can be rendered treatment to a level which can be reused. We may not use it for drinking, we may not use it for certain other useful purposes, but surely we can find several uses for this treated wastewater, and therefore reclamation of water is the only alternative for treatment and to overcome the water shortage. The, Now, out of these compulsions, the concepts and the philosophy emerges. And since water management is a social responsibility of all the water engineers, and it is our bounden duty to diligently ensure that we give a good water quality and we also implement good reuse and reclamation practices, we must do it. Traditionally, the Indian water supply is with municipal bodies, state water and wastewater boards, and there are a few industry organizations which have the control over water sources. They harvest water, treat it, supply it, and manage the wastewater. Now, reducing the quality and quantity of water in the traditional water sources throws up the reuse of treated wastewater as the only practical and viable alternative. And therefore, I would, in my opinion, call the wastewater treatment plants as the and consider them as the captive water sources of the utilities to which they belong. So then I come to my modified water cycle. The consequences of pollution by the wastewater and degradation of water sources is clearly the challenge of every country, every community, and the natural purification process of water in rivers, which are rivers and ponds and lakes and all other water bodies which are receiving contaminated water, and the pollution load is steadily increasing. So the purification processes, the natural purification does not happen. The bodies, they suffer from inadequacy and they are stressed. Stream sanitation, which was a natural process eulogized by Wells in his book on stream sanitation, has completely failed in today's world due to the pollution load. Therefore, we should draw the water reclamation cycle as a closed loop. This will also help in, the circular economy of water resources. So I take some water from the source, use it, it becomes wastewater, I take it to the wastewater treatment plant, treat it to a level that I can reclaim it, and this reclaimed water then goes in my water use stream, and I need to draw only the makeup water from my source. So this is my concept of the, you know, water cycle, the modified water cycle, if I may say so. Now, when we talk about water reclamation, there are several issues. Now, these issues could be technology related. They could be related to the process options, because there are several processes which I may take, several routes which I may take to reclaim water. I also have the issue of financial viability, which ultimately boils down to the life cycle cost per unit volume of water which I reclaim. My water demand is the issue, and this water demand is always increasing. It has been traditionally increasing since the millennia. The domestic water demand is increasing. Commercial, institutional, industrial water demand is increasing. This demand increase is inevitable because the commerce institutes of the nation, industries, they all contribute to the economy. And the economy has to be in the positive. Now, when I have reclaimed water, I also have the issue of its storage and distribution. Today, because of a single quality water systems, I have a particular storage and distribution network. As Dr. Pradeep very clearly brought out in his presentation, do I have the storage capacity? Do I have a distribution network? And how, if I don't have, then how am I going to plan, design, and implement this network? This network comes at all levels. It comes at the city level, it comes at the community level, it even comes at the single building level, because if I am recycling water, my building may require a dual plumbing system, one for fresh water, one for recycled water, if there is a qualitative difference. If I can bring it to the same quality, I may be able to work with a single stack system, a single plumbing system. Psychological and mental barriers, which in my opinion is the most vital issue when it comes to reclamation of water, is because people do not understand, and even if they understand, they do not want to appreciate the fact that it is the same water we are using today, which was used by our ancestors a million years ago. Water is neither created nor destroyed. We live in a closed system, and water is available to us in a fixed quantity, whether that will be in the form of ice or vapor or in the liquid form. That is a different issue. But the point is that we live in a closed loop, and yesterday's wastewater is today's water. Whether it is reclaimed using, the groundwater recharge, or whether it is reclaimed using the several technology and processes which are available to us today, is a moot point. And to overcome these psychological and mental barriers, it is very important that we take resort to information, communication, and education for awareness. And only then will we be able to overcome the mental barriers and the psychological block to use reclaimed water. Another issue here is that we need to build confidence among the consumers that what we are supplying is safe, will remain safe, and we are, using robust practices, processes, and technologies to ensure that the quality is not compromised, never. And there are luckily examples of robust quality, confidence building, and acceptance today available in a country like Singapore. I was talking about the imperative for reclamation and reuse. Now, since water is a matter of state policy, the state governments in India have got treated wastewater reuse policies. The first state to bring out the policy was Rajasthan, which brought out a policy in 2016. Policy laid down the guidelines for achieving 100% sanitation. It named wastewater as a resource and also stated that reclaimed water will be used for agriculture and industries with due safeguards. My own state, Maharashtra, was the second state for treated wastewater reuse. They stated that power plants and industrial establishments in the state will start using within a period of 3 years treated wastewater, and a time-bound schedule was laid down for this. Another progressive state of Gujarat brought out a policy in 2018, and they, under the policy, they hope to maximize the collection and treatment of sewage and other effluents, to use them on a sustainable basis, and a time-bound schedule has been laid down for full use of reclaimed water by 2030. Similar policies are likely to be brought in by other states, and perhaps even the central government will come out with reclamation policies and reuse policies of treated wastewater very soon. I now come to a few case studies of reclamation and reuse. I have been associated with some of these in my capacity as a designer. And the first one, which I love to talk about, is the case study of RCF Trombay. This is a wastewater treatment plant which is based on the raw domestic sewage generated in the Mumbai metropolitan area. This raw sewage is picked up from one of their pumping stations, and the treated product water of about 32 mld is generated, created, and used by the factory Rashtriya Chemicals and Fertilizers. This total 45 to 46 mld is treated in two streams. The first stream was generated in the early 90s, and it has primary, secondary, tertiary treatment, followed by reverse osmosis, pre-treatment, and reverse osmosis. The second stream, which I had designed, has only primary treatment, submerged MBR, ultrafiltration based, and reverse osmosis. And we are able to get excellent quality product water, which is used for the processes in the RCF plant. The second case study is that of Nagpur Municipal Corporation. It has a 130 mld sewage treatment plant. After primary and secondary treatment and some tertiary treatment, it is transmitted, it is conveyed to a power plant about 16 kilometers away, and it is used there. The third case study is of a sewage treatment plant in Surat. It is a 100 mld sewage treatment plant, of which 40 mld product water after primary, secondary, tertiary treatment and ultrafiltration followed by RO is used by the dyeing industries there. Udaipur Municipal Corporation and Hindustan Zinc Limited, they treat about 60 mld sewage, convert it into 40 mld product water after primary and secondary treatment, and use it. Some water is also discharged into a downstream lake. Chennai Metro Water has a sewage reclamation plant of 45 mld product water capacity with tertiary treatment and reverse osmosis, and this product water is supplied to industries in 25-kilometer radius. This project was initiated by the State Industries Promotion Corporation in 2009, and I had prepared the detailed project report for this. It was subsequently shelved, but was again made live and was commissioned last year, and 45 MLD product water is now being supplied. The next case study, this is under detailed planning and execution, is of Navi Mumbai Municipal Corporation, where two 20 MLD sewage treatment plants are being constructed for tertiary treatment, and this water will be supplied to the industrial estates within the corporation limits and around the corporation limits. Another case study is a greenfield project for a counter magnet city for Bangalore. A layout known as Nada Prabhu Kempegowda layout is being developed by the Bangalore Development Authority. Its water requirement every day is 150 million liters. And out of this 150 million liters, whatever sewage is generated, about 108 million liters of sewage will be recycled, reclaimed, and will be used for several purposes within this city. There are a total of 9 sewage treatment plants planned for primary, secondary, tertiary treatment. Capacity is ranging from 500,000 liters to 12.5 million liters per day. The recycle network for local reuse is also a part of this project, and this is under implementation. In one of my trips to the United States, I had the privilege to visit the city of Modesto wastewater reclamation plant. This is a 20 MGD plant, and the reclamation plant has an output of 15 MGD. This 15 MGD reclaimed water, after ultrafiltration based membrane bioreactor and UV radiation, is supplied to a 2,500 acre ranch through the local stream. And yes, never to forget, the Singapore Changi 2 design, build, own, operate project. This is a new water project with 228 million liters per day output, which is adopting advanced sewage regeneration technology using the double membrane treatment process of ultrafiltration and RO. This is followed by UV disinfection to convert sewage into potable water. This was commissioned in 2016. Here I come to the end of the municipal wastewater reclamation case studies. The preferred process for this is equalization, anoxic denitrification, aerobic denitrification, membrane bioreactor, UV radiation for disinfection, reverse osmosis, storage, and chlorination for distribution. I have listed some of the industrial wastewater reclamation case studies. These numbers which are given are for Abhishek Industries, Barnala, where 5 MLD of treated effluent from textile processing dyeing industries is reclaimed and reused. Welspun Group Anjar reuses 5 million liters per day. Alok Industries Vapi reuses 10 million liters per day. There are these other plants, one at Hassan, Ranjangaon. They use 5 and 6 MLDs respectively. Mahindra and Mahindra Nashik is an automotive manufacturing wastewater treatment plant of 1.5 MLD. After primary, secondary, and tertiary treatment, this entire wastewater is used for non-potable purposes. Trident Group Budni uses 10 million liters of treated effluent from dyeing and processing industries. And another big plant which is coming up for the dyeing and textile processing is a 110 MLD plant. This plant is under construction and will be completed in another couple of years. So across the length and breadth of the country, I have been lucky to be associated with so many reclamation initiatives, and the experience which I have gained in these initiatives uh, has given me the confidence to believe that reclamation can be the only answer to the problems of water shortages, water scarcities. My colleague Dr. Pradeep brought out a very pertinent issue, that is the issue of local reuse and de the issue of decentralization, that communities at the community level, towns at the town level, and small area metering areas, district metering areas, they should come up with their own treatment plants, so that the problems of huge transmission networks and the costs associated can be reduced. Now, uh, coming to the end of my presentation, during the last few decades, the concept of treated wastewater reuse and water reclamation has gained traction. Now, as we know, all our traditional water sources are either drying up or are in very bad shape, and they are not able to provide us the same quantity of water which they were designed for. The, the answers, they lie in reclamation and reuse. And I reiterate my point that all the wastewater treatment plants, they should be redesignated as our water sources, because we don't have any other. I am quite hopeful that the Jal Shakti Ministry, which is the Ministry of Water Resources and Water Regulators, they will bring out all the guidelines to rename all the sewage treatment plants, wastewater treatment plants as sewage reclamation plants or wastewater reclamation plants, and also provide a conducive framework for treatment of wastewater, reclamation, and reuse. I like to write on the work that I do, and I would like to share some of my articles which I have published during this lockdown, because this lockdown provided me an opportunity to uh, ruminate over the work being done by so many water professionals around the world. And I'm very happy to share these links with the presenters and with the attendees. And I'm sure I will welcome their reflections on what I have written. I am extremely grateful to Smart Water and Waste World for the opportunity, not just to present my work here, but also for the opportunity given to me to moderate the session and to be in the company of eminent engineers like Dr. Berrin Tansel, Dr. Srinivas Rao, Dr. Pradeep, and I will now have an open session for about 10 minutes where we can have a few questions answered. Uh, I will start with Dr. Pradeep. Dr. Pradeep, there is a question on how to remove microplastics to clean water from rivers and contaminated due to palm oil and mining waste.
Combined. Wow. So yeah, it's so for microplastics, particle size varies a lot, and so maybe membrane technologies is currently what you can do, but quantification of microplastic itself is a currently growing area. We have not yet understood what kind of microplastics, their particle size distributions, their defragmentations. We have recently started one PhD topic on documenting microplastic in wastewater. So we have one PhD student working on it. But on the treatment side, I think the ultrafiltration or nanofiltration will work, but that should be fine.
Another question. This is from Philippines. Dr. Berrin, the impact of COVID challenges on reuse, recycle, and also why is there a stigma attached to the reuse, recycle, or recycled water?
Well, recycled water is not a new concept. We have been drinking water that had been recycled for centuries. So it is just a matter of perception. As you had mentioned, Colonel, it's more of a psychological stigma. Recycled water is not necessarily a bad thing. It is actually much needed thing for sustainability. COVID impact, we have been seeing a lot of studies, as you had also mentioned, but COVID, the virus goes to the gastrointestinal system, and of course it gets into the wastewater, but we did not see live or like from the studies that we have been conducting in US and also I'm sure in India, worldwide, it had not been an issue in terms of potential contagious effects of the virus through wastewater. We did not see that.
Thank you. The next question, how to balance up the cost and benefits between various water reclamation and recycling technologies, especially when the effluent is from the industries?
Is it for me or Rao?
Yes, yes, doctor.
Oh, I mean, recycling is, of course, it's going to add to the cost, but it will also reduce the treatment cost for fresh water. So in the long run, if there is an optimum point that can be achieved. So it's going to be a learning and adjusting process. This is something out of necessity that we are dealing with, and we have to be in the quick learning mode at this time.
Next question for Dr. Rao. Dr. Rao.
Yeah, yes.
The brewery industries use huge volumes of water. However, available technology is very expensive to treat, and yeah, all the chemicals which are required are imported. This is a question from the Africans.
Well, the industry effluents, again, providing treatment to the applicable effluent quality standards is a must. And then, the reuse aspects of it. And then, there is also the zero liquid discharge, applications. So again, how you really envision various flows coming out of any industrial facility, that separating of the concentrated flows. So a lot of the homework that goes in there, and but industries are at the forefront, as we see in the US. How that matters at independent facility at specific levels. So all things are on the table, and specifically for industrial facilities, that's it. A day in, day out, that's a must to survive. In the economic world, what currently we see.
So no shortcuts. Whatever cost is there, it has to be incurred.
Yeah. Then again, the spin there is what I would contest is let us all try to explain the positive cash flow, what that means, how close we can get to.
True.
And you have to put your bearing to that positive cash flow and help the corporate world from the industry level, specific industry level. So that's a responsibility on our shoulders.
Thank you, Dr. Rao. The next one for Dr. Pradeep. Dr. Pradeep,
Yes.
this question
Yes.
is from Maharashtra. Maharashtra is facing drought in many places. Why reclamation is not planned to irrigate these areas to help the farmers suffering in such situation?
So there has been discussion about it a lot. Fortunately, Maharashtra has Maharashtra Water Resources Regulatory Authority, which is working on coming up with the regulations and guidelines to use this particular uh, sewage from the cities for the irrigation. There are many pilot projects are needed first to establish the practice, to establish the protocol for recycling, because only issue is the risk of pathogens and risk of heavy metals. Those need to be assessed. But I have been hearing that they are planning somewhere in the Marathwada region to have such kind of pilot project. But I think we need some enablers to push the industry, to push the cities, to push the government departments to come together and form these projects. I'm looking forward to be a part of it. But yeah, sadly, there is no much large scale success. You have very nicely presented, Colonel, that about some stories about where industries are actively involved. But we have not seen where cities and irrigation department or cities and other government department have worked together uh, to come up with this kind of reclamation projects. It's a need, but unfortunately, it's not yet there. We are stuck with the regulation. We are stuck with the political ecosystem, and the price. I think overall price of the water, how it is priced. It is wrongly priced, fresh water.
Thank you, Dr. Pradeep. I will take this one. This is about the industries and the treatment cost of effluent for recycling or treatment to such an extent that one can reuse this water in process becomes much higher. The basic issue is about the cost of treatment and the probability that if the cost is reduced, then this water use or reuse or use of reclaimed water will increase. Here, I would like to share with all our attendees the fact that when we talk about the cost of water, the actual cost and the cost which is charged was mentioned in passing by Dr. Pradeep about the fact that water is supplied at the rate of 3 rupees, where the production cost is 15 rupees. Now, for the industries, the same water, which has a production cost of 15 rupees, is supplied at a rate of 30 rupees or 40 rupees. Now, under the circumstances, it becomes very attractive for the industries to treat their water to an extent to which they want to use it. I can give another example of Bangalore, where in 2000, that is 2000 AD, the cost of water supplied to the industries was 60 rupees to a kiloliter, whereas it was under 5 rupees to a kiloliter for domestic supply. Now, if such is the cost differential, this supply rate to industries itself can become a deterrent for the industries to use fresh water, and they know that the cost of treatment and reclamation is much lower than this 60 rupees, and therefore the high cost of water supply to the industries can be one of the factors. But the domestic consumers should never forget that they are getting water at a very subsidized rate, which has no link whatsoever with the actual production cost of water. I think on that note, we can say goodbye to all the participants. Uh, to conclude, I wish to thank Dr. Berrin Tansel, Dr. Srinivas Rao, for joining us from the United States. We woke them up very early in the morning for this session. Thank you so much, madam and sir, for your efforts, for the cooperation you have displayed during in putting together, stitching together this webinar. Dr. Pradeep, thank you very much for your participation. Our thanks also are due to the technical administrators, Smart Water and Waste World, Mr. Mayur Sharma, Mr. Kailash Shirodkar, Bhaskar Chuvukula, and Mr. Ram Kumar. Thank you, ladies and gentlemen. It's been a pleasure to conduct this very, very useful, informative, and enlightening webinar. Thank you. Good morning.
I appreciate all.
Good evening to all the attendees. Thank you very much.
Thank you.
Thank you.
It has been an honor. Thank you.
Thank you.